Okay everyone, so I'm going to be making this video to just talk you through some inverse functions work for any student who missed the lesson on this. So inverse functions is something you experienced in GCSE as well. An inverse function does what it sounds, which is the reverse, the opposite of a function. So in other words, if you put some input into a function, you get an output, so typically going from x to get some output y, substituting that same output y in should get you back to the original function x. So if you put 4 into a function and you got 2 out, then putting 2 into the inverse function should get you 4 out. If we have a look at this in terms of a sort of rough mapping diagram, like we can see there, then we can see we've got our function f of x is equal to 2x plus 1. As we are starting to double our function and then to add 1 to it. The inverse then would be doing the reverse in the opposite order effectively. So we'd be starting by subtracting 1 to get back to 2x and then dividing by 2. So we got that our inverse function of x is equal to x minus 1 over 2. Okay, here's take a few seconds to think about this question, pausing it first. And then clicking play when you've had a chance to think and you think you've got an answer. Explain why the function must be one-to-one for an inverse function to exist. Pause and think about it. Well done if you realize that when we were looking at functions, we saw that there are only 2 mapping diagrams which lead to a function and there's one which does not. When we put an input into a function, we must have a specific outcome. If we can put one value into a function and we get more than 2 possible outcomes, then we've not actually got a function at all. A function is defined as you put one value in, you get one specific value out. So we can have one-to-one functions, like a standard straight line graph, and we can have many-to-one functions. So for example, y equals x squared, where there's more than one way to get a particular output, but nonetheless putting a specific input is always going to get you that same specific output. However, if we were taking the inverse of a one-to-many function, that would mean that taking the inverse might get you from the many to 1, and so it wouldn't be a function at all. So if the mapping has many to 1, then the inverse would be 1 to many, and we've not got a function at all. So you can only take the inverse of a one-to-one function. Now bear in mind that the domain for a function, which would otherwise perhaps be a one-to-many, would otherwise be a many-to-one for a domain of x, which is any real value in x, it may be that the domain is specified, for example, that x is always positive. So if we think about the typically many-to-one function y equals x squared, where there is more than one way to get a y coordinate of 4, for example, by substituting -2 in and +2, if that particular function is defined as only existent for positive values of x in its domain, then it's become a one-to-one function and you still can create an inverse function for it, but it only exists when that's the case. You cannot take the inverse of a many-to-one function, as the inverse of that would take you to a one-to-many, which isn't a function at all. Okay, more on inverse functions. So when we look at finding an inverse function, yes, you can make a sort of mapping diagram of sorts like we saw on the previous slide, but it makes more sense to instead use the skill that we're much more familiar and effective with, which is rearranging. So this might sound a bit, feel a little bit familiar from GCSE when we looked at inverse functions. What we should do, if I'm trying to find the inverse function here of f of x, which is equal to 3 minus 4x, is I should start by changing my f of x to be y, and then rearranging to make x the subject, and then at the end swapping my y's to be x's and my x to be f negative to the power of -1, so my inverse function of x. So let's just have a look at that. We'd have y is equal to my 3 minus 4x. I rearrange to make x the subject, and then at the end, instead of x, we write f minus 1 of x, and as we always typically have x as the value that we're substituting in, we replace our y for x here. I would pause and now have a go at this question here. Pause and have a go here. Okay, well done if you got this solution here. The key and the main reason I wanted you to have a go at this is, of course, that if you're not careful, you may forget that you need to factorize x out here in order to sorry, you need to factorize y out, my apologies. You need to factorize y out here in order to get x as the subject. Okay. I think it is x as a subject, actually, isn't it? Yes, eventually you got there. So yeah, subtracting your x here and adding your y, you're factorizing your x out, which allows you to make x your subject. I'm sure you got there quicker than I did by this point. Okay. So recapping the keys, the quickest and most effective way that uses the skills you've already got for finding an inverse function is to, instead of writing f of x, choose to write y, rearrange to make x a subject, and at the end replace your y with an x and your x, which is the subject right now, to be f minus 1 of x. That's how we find an inverse function. Now what's really interesting is what happens when we graph these inverse functions. Think carefully about what an inverse function is doing. When you put a x value into a function, you get a y value out of it, effectively, if we're calling x the input and y the output. Well, what do we know the inverse function does? Well, when given that particular y value, that inverse function will give you a particular x value. So what's happened? The x and the y values have swapped. Your x and your y values have swapped. What does this mean? This means, as usual in the black box, the domain of your function is the range of your inverse function and vice versa. So the domain of your function is the range of your inverse function, and the range of your function is the domain of your inverse function. Now if we plot this on a graph, what's it going to look like? What's it going to look like every time when we know the y's and the x's have swapped? Now these are symmetric. Look at them. They're clearly symmetric lines. And what do you think the line of symmetry is going to be? Pause and have a think about it. What's the line of symmetry going to be? Well done if you realised it's going to be y equals x. Alright, let's have a think about the domain of f here, looking at the diagram. Well, looking at the domain of my f of x function, it seems to exist for x values greater than 1. It looks like x equals 1 here is an asymptote, so that this function only exists for x values greater than 1. What does that mean about my range of my inverse function? That must also be for values greater than 1. So the only thing that's going to change here is just the fact that domain, we're always talking in x, so this is going to be for when x is greater than 1, and range is always in terms of the function, so I'll be able to say my f minus 1 of x is always going to be greater than 1. Okay, so that's just what this point here is emphasizing. We're still writing our domain in terms of x and our range in terms of the function or the inverse function, but importantly, otherwise everything has changed. Okay, everything has swapped. So the domain and the range swap for your inverse functions and your functions. Let's have a look at some examples now. So if g of x is defined as g of x is equal to the square root of x minus 2, for x being a real value that's greater than or equal to 2, calculate the range of g of x. Well, whenever we're finding the range of a function, we should start by considering the limits, if you like, considering the extreme values. Always a good mathematical strategy. So I would substitute 2 into this and consider what value would that give me. Well, substituting 2 into this, I'm going to get 2 minus 2, the square root of 2 minus 2 is the square root of 0, so that's 0. So when x is 2, this is 0. How about if I take x towards infinity, if I make x really large? Well, this is also going to become very large. If I get the square root of infinity, that's still a damn large number. So this will tend towards infinity as x gets larger. And so I can say that the range of g of x is that it is greater than that smallest value we found, or equal to it, which is 0. Okay, so that should be a g of x, sorry. Oops. update that. Okay. Calculate the inverse function. Well, you might want to pause and have a go at that. What's the inverse function of g of x going to be? I'm going to do the strategy we looked at before, so I'll write y is equal to the square root of x minus 2 and rearrange it. Okay, so rearranging, I'd get x equals y squared plus 2, and then I swap my x for my g minus 1 of x and my y for x there. Sketch the graphs of both functions. Now we should be relatively confident by this stage at sketching these functions. Let's start off with the slightly easier one. Sketching my inverse function, x squared plus 2, would be that classic U shape. I'm going to get that classic U shape. Let's just stick with that for the time being, and then have a look at what it actually looks like here. Okay, we've not got this negative part, so let's think about why that is. How about let's not dwell on that for too long yet. Let's think about sketching what y equals g of x is going to look like. Well, again, x is greater than or equal to 2, so it's going to start at 2 here. We figured out when we were considering the range that the smallest value here is going to be 0 when x is 2, and it's also a square root problem, so it's going to be increasing, but it's not going to be increasing in a hurry because we're always taking the square root of wherever the x coordinate is, minus 2. So what did we say, and what's the reason why this function here isn't our classic just x squared plus 2? We need to consider what the domain and range are of g minus 1 of x. Now we've already considered what the range was of g of x. So if the range of g of x is that it is greater than or equal to 0, that means the domain of our inverse is also going to be x is greater than or equal to 0. That's why it only exists in the positive, like we can see here. And how about the, so we've got the domain, what about the range of that? Well, the range of my g minus 1 of x is going to be equivalent to the domain of my original function. Well, my original function, I actually told the domain it's when x is greater than or equal to 2, and lo and behold, there's my range of my inverse function. It's when x is greater than or equal to 2. Okay, and whenever you sketch a function and its inverse function, you should be able to see quite clearly that these two graphs lines will reflect in the line y equals x. Now you might want to pause the video and just read through some of that, especially if it didn't seem very clear. I just spotted another typo, that this should be a G here too. You get the idea. Okay, let's have a look at one more example. The function is defined by f of x is equal to x squared minus 3 for real elements of x that are greater than or equal to 0. Notice by doing this, we've made it a one-to-one function. Okay, otherwise, even if we consider any negative values, it would not be. So as long as we define it as only positive values of x, this is a one-to-one function, and we can use it to find an inverse function. Finding our inverse function, you might want to pause and have a go at that. You should have said y is equal to your x squared minus 3, and then we're going to get x is equal to root x plus 3, and so on. So well done if you got that as your inverse function. Okay, we do that by rearranging and swapping. Sketch these functions now, and state the domain of your inverse function. Okay, well the domain of the inverse function is going to be the same as the range of the original function. What's the range of the original function? I would have to consider that by considering, well, what was the lowest possible value that this could be? The lowest possible value it's going to be is going to be when x is greater than or equal to 0, and that's going to be 0 squared minus 3. So the lowest possible value this can be is negative 3. What about as x tends towards infinity? This is also going to tend towards infinity too. So the domain of this is going to be that it exists for x values greater than or equal to negative 3. Okay, just like the range of this function is that f of x is greater than or equal to negative 3. Alright, that will be useful for our sketch. Sketching our original function f of x will also give us a clue for what this function will look like. I know it's going to be that classic U-shaped quadratic, but it's only going to exist for positive values of x. So I'm expecting this U shape here with a point here at negative 3. Ignore that, sorry. So I've got negative 3 here and negative 3 here. So I've got that U shape there, and how do I sketch my inverse function? Well, I know it's root x plus 3. I know that it's going to begin at negative 3 from considering the range of the previous function. I know that it's the range of the inverse function is going to be the same as the domain of the original function. Now the domain of the original function was that it's greater than or equal to 0, so the range of my inverse function should be greater than or equal to 0. We can see that it is. So sketching these two, we should see that it looks like they have a line of reflection on the line y equals x, and you might want to include that line as well to aid with what you're doing and to sort of try and interpret where they might both meet. And look at where they meet as well. This is very important. There's nothing to say that a function and its inverse function can't be at some point equal to one another. And that's why you might be asked to solve the equation that a function is equal to its inverse function. Now what you might be thinking, you might just want to pause a few seconds and think, what would I do if asked that question? So hopefully you've had a chance to have a think about this. What would you do if you were asked this question? Well, what you might choose to do is say x squared minus 3 equals root x plus 3. Fair enough, that's a relatively sensible mathematical thing to do. It's not a bad idea, but there's a trick, okay? There's a much easier trick to doing this problem, okay? Doing that method won't always get you a solution. It certainly will take longer than this solution, which is consider that the only time, due to that line of symmetry, the only time that a function is going to be equal to its inverse function is on the line y equals x. And so the only time when this is going to be equal to this is going to be the same as when this is equal to x. So when f of x is equal to x, when y is equal to x, that is when we can solve that the function of x is equal to the inverse function of x. That's a very important thing to note down and remember. Okay, if you're trying to solve when a function is equal to its inverse, you can take a shortcut by just saying I'm trying to find when it's equal to x, which is laid out again here. Okay, so by equating this original function to x, I don't think it's extremely clear here, so let's just make that clear. We're going to have x squared minus 3, that's our function, equals x, which we could then rearrange to be our x squared minus x minus 3 is equal to 0 and solve. That is a lot quicker than solving my x squared minus 3 is equal to root x plus 3. Alright, so just bear that in mind for when you're trying to solve these two. Okay, take a few seconds to have a go at this problem here, and then click play when you're ready. The function f is defined by f of x is equal to e to the power of x plus 2 for real values of x. Find the inverse function and state its domain. And then on the same axis, sketch the curves with equation y equals f of x and the inverse function of x, given the coordinates of all the points where the curves cross the axes. Well, for the first part of this, we're going to let y equal e to the x plus 2 and rearrange to make x our subject, and then remember to swap out x for f minus 1 of x, and that's going to be equal to log natural x minus 2. Stating its domain would mean we had to consider what the range is going to be of this original function. Now the range of this original function is if it's for any real value of x, we would have to consider what is the smallest possible value that this function can take and the largest possible value that this function can take. Well, the smallest value it can take would be if we took x towards negative infinity here, e would tend towards 0. So the smallest value would be 2. In fact, it would be just slightly larger than 2. It never, as this tends towards 0, it never gets to 0, so the smallest value would be tending towards 2. So the range of this function is that it's greater than 2. And so, stating its domain, the domain of this function must be for x values greater than 2. So we write x is greater than 2 here. Now how about on the same axis, sketching the curves y equals f of x and y is equal to the log natural minus 1 of x. We're expecting these to reflect in the line y equals x. We need to sketch and include the key intercepts, so the easiest one to sketch here would be e to the x plus 2. We know when that's going to intercept the y-axis when x is 0, which would give us the coordinate 0, 3. We know it's that classic exponential where it's going to tend towards infinity. and our logarithmic graphs, which are less less practiced in sketching. We know it exists for x values greater than 2 from our work in the previous question. So we'd have an asymptote at 2, just like we'd have an asymptote at 2 on the line y equals 2 here, and we get this sketch here. Okay, notice the how the marks are broken down for this exam paper question. You get a mark for the general shape of both of these and a mark for the key intercepts. In this case, there's only 2 key intercepts. The shape would include some sort of indication that you understand there's an asymptote. I think it's been relatively generous that you've not had to state the asymptote. I think you should always do that, just in case. But you certainly should show an understanding that you know there is an asymptote there. Okay, now you'll have seen from the lesson the exercise D2D questions that I'd like you to have a go at. I hope you found this talk through helpful.